Exoplanets and habitable zones. Exoplanets, or extrasolar planets, are planets that orbit stars other than our Sun. The discovery of exoplanets has revolutionized our understanding of planetary systems and the potential for finding habitable environments beyond our solar system. Detection methods. Scientists use various techniques to detect exoplanets. These include the transit method, which measures the slight dimming of a star as a planet passes in front of it, and the radial velocity method, which detects a star's wobble caused by the gravitational pull of an orbiting planet. Other methods include direct imaging, gravitational microlensing, and astrometry. Direct imaging. Direct imaging involves capturing images of exoplanets by blocking out the bright light of their host stars. This method is useful for studying larger, more massive exoplanets that are located farther away from their stars. Gravitational microlensing. Gravitational microlensing occurs when the gravitational field of a foreground star magnifies and brightens the light of a background star. If a planet orbiting the foreground star is present, it can cause additional deviations in the observed brightness, indicating the presence of an exoplanet. Astrometry. Astrometry involves measuring the precise position and motion of a star over time. The presence of an exoplanet can be inferred by detecting the small, periodic shifts in a star's position caused by the gravitational influence of an orbiting planet. Other methods. There are additional methods used for exoplanet detection, including the transit timing variation method, studying the timing variations of transit events caused by interactions between multiple planets in a system, and the pulsar timing method, monitoring the pulsations of pulsars to identify changes caused by orbiting planets. Exoplanet characteristics. Exoplanets come in a wide range of sizes, compositions, and orbital configurations. They can be rocky like Earth, gaseous like Jupiter, or even have unusual compositions. Some exoplanets orbit close to their stars, hot Jupiters, while others reside in the habitable zones. Size. Exoplanets come in a wide range of sizes. They can be similar in size to Earth, terrestrial or rocky planets, larger like gas giants such as Jupiter and Saturn, or even larger than gas giants, super-Jupiters. Composition. Exoplanets can have diverse compositions. Terrestrial exoplanets are typically composed of rocky materials like silicates and metals. Gas giants are primarily composed of hydrogen and helium, with possible additional components like water, methane, and ammonia. Atmosphere. Some exoplanets have atmospheres, which can vary greatly in composition. The presence and composition of an exoplanet's atmosphere can be determined through spectroscopic observations, providing insights into its potential habitability and atmospheric conditions. Orbital characteristics. Exoplanets have different orbital configurations. They can have short orbital periods, orbiting very close to their host stars, hot Jupiters, or have long orbital periods, residing in the habitable zones where conditions for liquid water may exist. Habitable exoplanets. The search for potentially habitable exoplanets focuses on identifying planets within their star's habitable zone, where conditions may allow for the existence of liquid water on the planet's surface. However, habitability is a complex concept, and factors like atmospheric composition, presence of a protective magnetic field, and other environmental conditions are also important. Habitable zones. Habitable zones, also known as Goldilocks zones, refer to regions around the star where conditions are suitable for the existence of liquid water, a key ingredient for life as we know it. Here are some details about habitable zones. A habitable zone is defined as the orbital region around the star where the temperature is within the range that allows liquid water to exist on the surface of a planet. This zone depends on factors like the star's size, temperature, and luminosity. Inner and outer boundaries. The habitable zone has an inner and outer boundary. The inner boundary is defined by the point where the greenhouse effect becomes too intense, leading to a runaway greenhouse effect like on Venus. The outer boundary is where the planet's surface temperature drops below the freezing point, resulting in a state similar to Mars. Inner boundary. The inner boundary of the habitable zone is the point closest to the star, where conditions are still suitable for liquid water to exist on the surface of a planet. If a planet is located too close to its star, it experiences intense heating, leading to a runaway greenhouse effect. This effect occurs when the planet's atmosphere traps an excessive amount of heat, causing the temperature to rise to extreme levels. Venus, for example, is an example of a planet experiencing a runaway greenhouse effect, with surface temperatures averaging around 900 degrees Fahrenheit, 475 degrees Celsius. Outer boundary. The outer boundary of the habitable zone is the point farthest from the star where conditions still allow for liquid water on a planet's surface. If a planet is located too far from its star, it receives insufficient heat, resulting in temperatures dropping below the freezing point of water. This leads to the planet being in a state similar to Mars, where liquid water is not stable on the surface. The habitable zone is often described as a Goldilocks zone, since it represents a region where conditions are just right for the existence of liquid water. However, it's important to note that habitability is a complex concept and depends on various other factors, such as the planet's atmosphere, composition, presence of a magnetic field, and the potential for surface water retention. These factors play crucial roles in determining the overall habitability of a planet. The boundaries of the habitable zone can vary depending on the properties of the star, such as its size, temperature, and luminosity. Scientists continue to refine our understanding of habitable zones and explore the potential for life in environments that may exist beyond the traditional boundaries. Considerations for habitability. While being within a star's habitable zone is an important factor, it doesn't guarantee habitability. Other factors, such as the planet's atmosphere, composition, presence of a magnetic field, and potential for surface water retention, play crucial roles in determining habitability. Exoplanets in the habitable zone. Scientists have discovered exoplanets within the habitable zones of their host stars. Examples include Proxima Centauri, b TRAPPIST-1 system, Kepler 452 bits, and many more. These discoveries have sparked excitement and further investigations into their potential habitability and the search for signs of life. The study of exoplanets and habitable zones has revolutionized our understanding of planetary systems and the potential for life beyond Earth. Discovering exoplanets and characterizing their habitability expands our knowledge of the diversity of planetary systems and informs our search for life elsewhere in the universe. Continued research, observations, and advancements in technology will provide further insights into the conditions required for life and the potential habitability of exoplanets. That's all in this video. If you like the information, please hit like and subscribe to this channel, and be connected to this channel for more space information.